Hey guys, this is the missing content from the other lecture that you have, and I want to look at the gas-filled swim bladders. We have a physiostomus and we have a physoclistus. So the first one is the bladder mouth, and so if you can draw a picture of the bladder mouth. Here is the fish. Just do kind of a sketch like this. Here's the eye. Here's the mouth. And the air bladder exists right about here for fish. So connected to the mouth is the esophagus. The esophagus will then connect to the stomach, which will then go to the anus for excretion. In a physiostomus, you have what's called a pneumatic duct. So this right here, this is the air bladder, and this structure right there is the pneumatic duct. And of course, this is the mouth, and there is the esophagus. So in the lecture it was described that when this type of fish needs more air in the air bladder, they can actually gulp air through the mouth. The air will go through the esophagus, connecting to the pneumatic duct, and then the air bladder can then get filled with air. However, if it's at the depths, it also has what's called this gas gland. And this gas gland is connected to the blood supply, which is going to be connected to the heart, the circulatory system. And at the deep depths, you can't gulp water because there's no air. So we need to find another means of inflating this air bladder, and the blood coming in can then release the oxygen to fill up the air bladder. And the air bladder can then expand. So that is a physiostomus, the bladder mouth. Now the physoclistus, you can draw your fish in the eye, mouth. Don't need to rename the air bladder. And here's the esophagus, stomach, anus. But you'll notice there is no pneumatic duct. So there's no pneumatic duct. So this guy cannot gulp air. This guy cannot burp air either. If it's trying to release the gases, it can't fart out the air either. This one can burp the air out. The air can get forced through the pneumatic duct, through the esophagus to the mouth, and that's when fish will produce bubbles, or they can actually, it can also go this way, take a little bit longer going through their digestive system, but they can also fart out bubbles as well. This one can't do this. So again, this is a physiostomus, the bladder connected to the mouth, and a physoclistus. And this one can also absorb the oxygen into the air bladder to inflate it. And we can also go the reverse. When ascending, this one can also go the reverse by absorbing the oxygen back into the blood. Both can do that since they both have this gas gland, but this one has an extra feature with the pneumatic duct to release air bubbles. So that's with the bladders. We also took a look at the counter current exchange system. Okay, so the counter current exchange system I want to first show you the non-countercurrent exchange system in your notes. Okay, so you have two different sides. So here is going to be the countercurrent. Okay, and then you also have a space to draw the non-countercurrent. I want to show this one first. It's a little bit easier to draw. If you remember from the lecture, we have a 6 parts per million concentration of oxygen that's in the water. So this is going to be entering into the fish's mouth, which will then go to the gills. So imagine the gills with the blood vessels are coming in with completely deoxygenated blood to meet this 6 parts per million water. So it's coming in at 0 parts per million. So this is going to be the gill down below here, and this is the water that's passing over the gills as it comes into the fish. So here we have 6 parts, and here we have 0 parts. Well, if you remember from biology or chemistry, things are going to move from a higher concentration to a lower concentration. I think we also talked about this with diffusion and osmosis. So the oxygen is going to diffuse from the higher concentration to the lower concentration. So imagine that the 6 parts per million is going to lose 1 part per million to the gill. The water will then be 5 parts per million, and now the gill has gained 1 part per million. So it's gone from 0 to 1. You'll notice that there's still a higher concentration in the water compared to the gill, so the same thing will happen. The water will lose 1 part per million, okay, and the gill will gain that 1 part per million. So the gill is getting more oxygenated with oxygen. So we still have a difference from 4 to 2, so we have losing 1 more part per million, 3, and it will become 3 parts per million. But you'll now notice that the concentrations are the same, so there's not going to be diffusion one way or the other. So in this scenario, with a non-countercurrent exchange system, which doesn't exist, this is just an imaginary system, the maximum you can get is 3 parts per million. 3 parts per million, and that's going to be the max that you can get from this. So now let's take a look at the countercurrent exchange system. This is what exists in fish. And we have the 6 parts per million coming in to the mouth again, except instead of the blood vessels running in the same direction as the water, it's running against in the opposite direction, like this. Okay, so here's the blood vessel, okay, within the gill, okay, except now the blood vessel's running in the opposite direction. That's why it's called counter. Counter means going against. So it is coming in with a 0 parts per million because it's going to be deoxygenated. And we sort of have to just draw this the way that it is. So it's going to counter the water until it absorbs 1. It'll absorb another part per million at 2, and 3, and 4, and even 5. Because this is what the concentrations of the water is going to be. It's going to be 6, it's going to lose 1, become 5, it's going to lose 1, it's going to become 4, it's going to lose 1, becoming 3, it's going to lose 1, becoming 2. Okay, it'll even lose 1 here. Okay, but you'll notice that the concentration of oxygen in the water is always higher than it is in the gill. So in each of these phases, so what's going to be happening is this 0 concentration is going to gain the 1. So now that it's 1, okay, and it's encountering water that has a concentration of 2 parts per million. As it continues along, it's going to be absorbing 1 part per million from this because it's a higher concentration. So now it's going to have 2 parts per million. It's encountering water with 4 parts per million, so it's going to be absorbing 1 part per million. Now it's 3 parts per million. It's going to be encountering water that has a higher concentration, so it's going to be 5 parts per million. So the oxygen will again diffuse into the gill. The 4 will be encountering water that's 6 parts per million, so it's going to diffuse across and become 5 parts per million. So with the countercurrent exchange system that we see in the gill, the blood vessel is always encountering water with a higher oxygen concentration, which will enable it to absorb more oxygen. This enables it to absorb 5 parts per million maximum. So the countercurrent exchange system is more efficient than this. This doesn't exist. This is the one that does exist.